Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler, and today we'll be doing Unit number 9, Lesson number 9 on equations of circles. Now, this probably, when you hear the title of this lesson, your mind might drift to things like area equals pi r squared, or the circumference equals pi times the diameter of a circle. These are formulas that calculate things about a circle: its circumference, the distance around it, its area, the space inside of it. But these aren't the equation of a circle. When I talk about the equation of a circle, I want an equation that relate the x and y coordinates on a circle that's plotted in the coordinate grid. This is no different than plotting or understanding the equation of a line. So that's where we're going to actually begin today, is revisiting an equation of a line so that you kind of understand what's happening with the equation of a circle. Let's jump into it now. All right? Now, recall that an equation that relates two variables, x and y typically, simply describes a relationship between them. It simply says, hey, when I have this x and this y on these curves, whether it's a line, a circle, a parabola, or anything else, there's some relationship between them that's always true. All right? So let's take a look at this for this line. Now, in this lesson today, if you're working from our worksheet, this isn't anywhere on it. This is just trying to lead you into the idea of an equation of a circle. So, taking a look at this line, blue line plotted with all these red dots, the first question I want to know is, what's true about every point on this line? Well, take a look at some of them. For instance, this point right up here, right? That's the point 0, 7. Right? I don't know. There must be something true about that. This is the point 1, 6. Here we've got the point 2, 5, and the point 3, 4. And I don't need to keep listing them. Those are just some of the points that lie on this line. Now, ask yourself for a second, what is true about the relationship of x and y in each one of these 4 points? Well, hopefully it's obvious. When I take the x-coordinate and the y-coordinate and I add them together in each case, I get 7. I get 7, right? Their sum is the sum of x and y is 7. Now, if I ask you for the equation of this line, you might start thinking about y equals mx plus b. You might start saying, well, the y-intercept is 7 and the slope is -1, so I can do this and that. But at the end of the day, the equation that relates x and y for this line is simply x plus y equals 7. That's its equation, because it relates every xy point on this graph. Every point on this graph, the x-coordinate plus the y-coordinate is 7. So what we want to do with circles and equations of circles is we want to come up with a condition that is always true for a given point on a given circle. So now let's jump into exercise 1 and take a look at how that works. All right, here we go. Now, so that we don't take up too much space, I've got a circle here and I've really only graphed a portion of it. Okay, the rest of it kind of would be down here and it would overlap a bunch of the text and we wouldn't want that. But let's take a look at exercise 1 and what it asks. In the grid below, a portion of the circle whose center is at the origin, important, and whose radius is 10, also important, is drawn. Answer the following questions. What is true about every point that lies on this circle? So very similar to that problem with the line that we just had. What's true about every point that lies on this circle? Pause the video now and see if you can write something down. All right. Well, what is the definition of a circle? The definition of a circle is it's all the points that are a fixed distance, the length of the radius, away from a fixed point, the circle's center. So what's true about every single point that lies along this circle, not just the nice ones, but even the ones with messy, messy coordinates, what's true about every single point along this circle is that they lie 10 units from the origin. Or you could say that they're a distance of 10 units from the origin. All right? But that's true of every single point on this circle. So take a look at the next question. Algebraically show that the point 6, 8 must lie on this circle. All right. Well, what does it mean for the point 6, 8 to lie on this circle? Well, here it is. Now, that's not what we mean by algebraically show that it lies on the circle. But to show that the point 6, 8 lies on this circle, what we can do, really, is we can work with this. That was a terribly drawn right triangle, but we can work with this right triangle, right? Specifically, a right triangle, right, that has this is 6, this is 8, and this is 10, right? So really, to show that this point lies on the circle, we just have to make sure that 6 squared plus 8 squared is equal to 10 squared, right? Because for every single point on this circle, we can draw one of these right triangles in. Maybe we can draw it in pretty poorly, like the one I did in blue, but we can draw one of these triangles in. And in fact, 6 squared is 36, 8 squared is 64, 10 squared is 100, 36 plus 64 is 100, and therefore we have it. You could also use the distance formula, and we're going to use that later on in this lesson. But for right now, especially because the center of our circle is at the origin, we can really just think about this in terms of a right triangle. All right? Now, letter C says, it appears that the point 7, 7 lies on this circle. Does it? Justify your response. So think about this for a moment. Does 7, 7 lie on the circle? Well, the answer is no, all right? And it's no because if we draw this right triangle, right? And again, what it means for the point 7, 7 to lie on the circle would be then 7 would be here, 7 would be here, and we would have a hypotenuse of 10, all right? Well, does that work? Is 7 squared plus 7 squared equal 10 squared? Remember, this is just simply the Pythagorean theorem. Well, then we get 49 plus 49 is equal to 100, 98 is equal to 100, and therefore the answer is no. The point 7, 7 doesn't lie on this circle. Okay? Finally, letter D. If the point xy, so now a generic point, xy, lies on this circle, write an equation that must be true involving x and y based on the right triangle shown above, or more appropriately, shown right here. So here's the thing, right? Just like the equation of that line where x plus y was equal to 7, in this case what we really have is we've got a situation that looks like this. All right, for every single point that lies on this circle, because it's centered at the origin, and this distance is x, and this distance is y, and this distance is always 10, we can simply write down the Pythagorean theorem for this right triangle that says x squared plus y squared is equal to 10 squared, or better yet, x squared plus y squared is equal to 100. And this is then the equation of that circle. That's it. Now you might say, well, really? That's the equation of a circle? And it in fact is. That's it. And you can use that equation then to test to see if any other point lies on that circle, right? If you wanted to know if some random point like 3, 8 lied on the circle, you could say, well, is 3 squared plus 8 squared 100? The answer, by the way, would be no, but you could then test that to see. All right? And that's the main purpose of an equation for something like the equation of a circle, is to be able to then check to see if particular points lie on the circle by seeing if they make the equation true. All right, so let's kind of summarize what just happened here. This is only for equations whose centers, for circles whose centers are at the origin. But a circle whose center is at the origin, 0, 0, and whose radius is r, will always have an equation x squared plus y squared equals r squared. All right? And again, if this looks a lot like the Pythagorean theorem, a squared plus b squared equals c squared, it's because it is, right? Because what you really have in this situation is you really have a situation where for any point, right, x comma y, you've got a leg of the right triangle here that's x, a leg of the right triangle here that's y, and then its hypotenuse is r. So x squared plus y squared equals r squared. Simple. If circles are centered at the origin. And many times, especially strangely enough in higher level math, they are. You know, they're just centered at the origin, and all we really need to do is be able to describe them using this Pythagorean theorem. All right? But of course, even more importantly, is what happens if they're not centered at the origin. Let's do one more, though, that is centered at the origin, and then we'll move on to the more challenging ones. The point 7, 4 lies on a circle centered at the origin. Write the equation of the circle and state its radius. All right, well, since the circle is centered at the origin, it's going to have a general equation of x squared plus y squared is equal to r squared. Okay, every circle centered at the origin has this general equation. So really, the question then is, how do we figure out what the rest of this equation is? And we can do that by an old trick that we saw back in Algebra 1 and that you'll use a lot as you kind of move through in mathematics, which is that we know that this point lies on the equation of the circle, so we can substitute it into the circle. We can say, okay, well, I'm going to put 7 in there, and I'm going to put in 4 there. All right, and that's going to be 49 plus 16 equals r squared. That means I've got 65 is equal to r squared, and r, which they ask about, is the square root of 65. All right, state the radius. There it is. But the final equation of this circle, which we also want, is x squared plus y squared equals 65. This is the equation of that circle. Now remember, it's not x squared plus y squared equals the square root of 65. This number is always the square of the radius, not the radius itself. And yeah, it would have been nice had it been 64, because then the radius would have been 8. But it wasn't. It was 65. Now, letter B asks, is the point -8, 1 also on this circle? Justify your answer. Well, see if you can figure this out. Pause the video now and take a few minutes. All right, well, let's take a look. A point lies on the equation of whatever: a line, a parabola, a circle, an ellipse, a hyperbola, 3-dimensional objects, 4-dimensional objects, it doesn't matter. A point lies on the equation of blah if, when you substitute it into the equation, it makes it true. So the equation of our circle, I'm going to just rewrite it down, is x squared plus y squared equals 65. So now if I want to know whether this point lies on the equation of this circle, I simply substitute it into this equation. -8 squared is 64, 1 squared is 1, and 65 equals 65. So the answer is a resounding yes. Absolutely. Right? If the point makes the equation true, it lies on the graph, and if the point makes the equation false, it doesn't. All right, never forget that truth about graphing. It's very important. All right, let me step out of the way, give you a moment, then we will move on to start to examine circles that aren't centered at the origin. All right, let's do it. Here we go. So, circles not centered at the origin. Now, the key for circles not centered at the origin truly will be the distance formula. And remember how the distance formula works, okay? If x1, y1 is one point, and x2, y2 is another point, then the distance between those 2 points is always taken by finding the difference in the x-coordinates, squaring it, finding the difference in the y-coordinates, squaring it, adding them together, and taking the square root. Don't forget that this truly is the Pythagorean theorem, just like the equations of the circles we've already seen. The distance formula is also just the Pythagorean theorem, basically used to find the length of the hypotenuse between 2 points in the coordinate grid. But let's see how that connects now to the equation of a circle. Exercise number 3. Consider a circle with a center at 4, 2 and a radius of 5. Show that the points 8, 5 and 1, -2 must both lie on this circle. Well, again, the definition of a circle is it's the collection of every point that is a fixed distance away from a fixed point. So if these 2 points are on this circle, then when I find the distance between this point and this point, I should get 5. So let's take a look at that for this point, and then we'll have you do that one by yourself. All right, I want to find the distance between 4, 2 and 8, 5. All right, well, the distance formula will be the square root of x2 minus x1 squared plus y2 minus y1 squared. So 8 minus 4 is 4 squared. 5 minus 2, is 3 squared. All right, I'm going to run out of space here pretty quick. That's 16 plus 9. That's the square root of 25, and that's 5. So you bet. This point, 8, 5, is 5 units away from 4, 2. Since that's the center and the radius is 5, that point must lie on the circle. Why don't you go ahead and do the same thing with the point 1, -2, and then we'll go through that quickly. All right, remember, we're checking to see if 1, -2 lies 5 units away from 4, 2. All right, so yet again, we've got 4, 2 and 1, -2. I just want to find the distance between them. All right, between the center and a point, 1 minus 4 squared, -2 minus 2 squared. We've got more negatives we have to deal with in this problem. Hopefully not too bad for you though. 1 minus 4 is -3 squared. -2 minus 2, watch out, is -4 squared. Always remember, when you square a negative, you get a positive. -3 squared is 9. -4 squared is 16. That gives us again the square root of 25, which is 5. So yes, right? This point lies 5 units away from the center, therefore must lie on this circle. Now how do we take this though and come up with the equation for this circle? It's actually relatively easy. Let's take a look at letter B. Extend the page a little bit. So here we've got that circle, right? Its center is at 4, 2, its radius is 5, and now what I do is I take an arbitrary point, the point x, y. All right? It says given that x, y is an arbitrary point on the circle, write an equation for the distance this point is away from the center. Rearrange the equation so that it contains no radicals. All right, so just like we did before, let's take the point 4, 2, but instead of having some point whose coordinates we know, we take a generic point, right? And what we say is, well, the distance between these 2 points will be the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, one thing that's kind of cool, if I can get rid of all these boxes, is that I know that this distance is equal to 5. So I'm just going to write this down as equal to 5, right? That's what the distance is equal to. Now notice it says rearrange the equation so that it contains no radicals. Well, in order to get rid of the radical on the left-hand side, all I have to do is square it, right? Squaring and square rooting are inverse operations. They undo each other. You know that already. When you have x squared equals 64, you take the square root of both sides and you get x equals plus or minus 8. Here we have the square root of I don't care equals 5. So to get rid of the square root, I square both sides. Literally, those two cancel. And I'm left with x minus 4 squared plus y minus 2 squared is equal to 25. And this is the equation of that circle. Every point on that circle will make this equation true, including the 2 points from up here. We could check that, but in essence, we already did. This formula is simply the result of the distance formula between an arbitrary point, like xy, and the center, 4, 2, and setting that distance equal to 5, and then squaring simply to remove the square roots. Keep in mind, this formula still has the structure of the Pythagorean theorem. something squared plus something squared equals the radius squared. And it's very, very similar, in fact, to circles centered at the origin, right? A circle centered at the origin looks like this. All right, this is still r squared, right? So no difference there. The radius was 5, that's 5 squared. The difference is that we've got some subtraction going on here, and specifically, we're subtracting the center coordinates of the circle. That gives rise now to the equation, the general equation of a circle. And it's really cool. Students love equations of circles because they're very, very easy to deal with. If a circle has center coordinates of x sub c, y sub c, and anytime you've got these little subscripts like this, okay, little subscripts, it means we're talking about a specific point. Here we're talking about the point that's at the center of the circle. So we've got some circle with center coordinates x, c, y, c, and whose radius is r. Then what we do to find the equation of the circle, not find it, but just write it, is do x minus its center coordinate squared plus y minus its center coordinate squared equals r squared. That's it. Now, the first thing that you have to be able to do with equations of circles is take them and identify the center and identify the radius. So let's take a look at that in exercise number 4. It says, for each equation below, state the circle's center and radius. Well, when we look at this particular equation, right, x minus 5 squared plus y minus 2 squared equals 25. And let me actually put the general equation down here so that we've just got it sitting on the screen. All right, it's pretty easy, right? The center, which I'll denote as c, is 5, 2. Right? We've subtracted 5, we subtracted 2, so the center coordinate is 5, 2. Okay. And the radius is going to be 5, because this is the radius squared. All right, so very easy. Center at 5, 2, radius of 5. But let's take a look at letter B. Letter B says x plus 4 squared plus y minus 1 squared equals 100. Now that's trickier, because we're looking for subtraction, x minus its center, y minus its center. The radius is still easy. The radius squared is 100, so the radius is 10. No problem, okay? In fact, even the y minus 1, not a problem. Y minus y sub c, so the center coordinate of y is 1. What do I do with this x plus 4? Well, let me just suggest that I could write this as x minus negative 4 squared plus y minus 1 squared equals 100, right? If I write it like this, x minus negative 4, which is the same as x plus 4, then I can see that the center of my circle has coordinates of negative 4, 1, and my radius is 10. All right? Simple enough. Now, what many students will start to do, very understandably, is they'll say, look, I'm going to look inside the parentheses and I'm going to kind of take the opposite of what I see. In other words, when I see x plus 4, that's going to tell me the x coordinate of the center is at negative 4. When I see y minus 1, that's going to tell me that the y coordinate is at positive 1. And that certainly works. There's no question about it. Let's take a look at another one, though, that's kind of weird. X squared plus y minus 3 squared equals 1. Again, the radius is no problem. The radius squared is 1. The radius is also 1. But this one's a little weird, just x squared. So what would be the x coordinate of the center? It would be 0. Okay? And again, the reason why is that you could rewrite that x squared as x minus 0 squared. You don't have to. Most students probably won't even do that because they'll just recognize, all right, if there's nothing being added or subtracted to the x, well then the x coordinate of the center is 0. Fair enough, right? In fact, I can now say the center is at 0, 3, and the radius is 1. All right, maybe I'll circle these as well so you can see them. See if you can complete the last 3. Pause the video now. All right, let's do it. Well, for this one, since we have x plus 4 squared, let me Get rid of a little bit of that so you can see it. Since I have x plus 4 squared plus y squared equals 16, I can say that the center is at negative 4 comma 0, and my radius is 4. All right? Here, we've just got a circle that's centered at the origin. X squared plus y squared equals 9. My center is at the origin, 0, 0, and my radius is equal to 3. Easy enough. And finally, x plus 2 squared plus y plus 5 squared equals 81. My center will be at negative 2, negative 5, and my radius will be equal to 9. All right, that's it. It's as easy as looking at the equation of a line and pulling off its y-intercept and its slope. All right? Probably the trickiest thing for many students is that because you're subtracting the coordinates of the center, x minus x sub c, y minus y sub c, when you have addition, like this x plus 4, better yet, even this last problem, x plus 2 squared plus y plus 5 squared equals 81, you have to think of it as x minus negative 2, y minus negative 5. Or, as I mentioned, many students will simply say, I'm going to look in the parentheses and I'm going to take the opposite of what's sitting there. X plus 2, x coordinate center, negative 2. Y plus 5, y coordinate of the center, negative 5. That's okay. All right, let me step out of the way for a second, write down any of these answers that you didn't get the first time, and then we'll move on to more problems. All right, let's do it. So, actually, we're wrapping up. All right, and we're wrapping up because we wanted to keep the first lesson on equations of circles fairly simple. In the next lesson, we'll kind of get into them more deeply and we'll do a little bit more with equations of circles. Keep in mind that the equation of a circle, right, like equations of lines and parabolas, simply gives you a description of all points that lie on the circle. The interesting thing, though, is that equations of circles come directly from the Pythagorean theorem or the distance formula. Again, that's the Pythagorean theorem, but it's interesting to note that you always have something squared plus something squared equals something squared. A squared plus b squared equals c squared. Circle centered at the origin, x squared plus y squared equals r squared. Circles not centered at the origin, x minus x sub c squared plus y minus yc squared equals r squared. All right, you're going to get some work with that. Pretty easy homework, I hope, in this lesson, and then you'll be ready for the next one where we have to do a little bit more analysis. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.